It's comments in this one.
Okay, so to review last time, we found that the Dirac equation here would reproduce the Klein-Gordon equation if these objects were matrices satisfying a Clifford algebra, this anti-commutator relation giving twice the Minkowski metric times the identity. Now, that relation, suppose we find one set of matrices that satisfy this. Then let a general gamma be given by a similarity transformation. Any element of GLNC, or GL4C, the general linear group in 4 complex dimensions, if I multiply by one element here and its inverse there, and substitute to find the anti-commutator of these new gamma matrices, then expand out, what happens is that A inverse here just gives the identity and just leaves the outer A and A inverse on each term, so that we have the outer A and A inverse sandwiching the anti-commutator of the original gamma zeros, which we know is twice eta times the identity. And the similarity transformation of the identity, of course, is just the identity. And so if these gamma zeros satisfy the Clifford algebra relation, then any gammas related by a general linear similarity transformation also satisfy it. Then, last time, we found a particular set of matrices. These are 2 by 2 submatrices built from the Pauli matrices and the identity, and we argued that these satisfy those relationships. So, given that we have one set of matrices that satisfy it, we can find infinitely many more. And in fact, it becomes possible if we prove things using this representation. So, for example, let me define gamma 5 to be a multiple of a product of gamma 0, gamma 1, gamma 2, gamma 3. And I can write that as a gamma 0, 0. So if we go to this, back to our basic representation, the same kind of argument holds. 1 A inverse. You can see that all the A inverses here are going to cancel. So these adjacent pairs of A's and A inverses just give identities. And we're left with A gamma 5, A inverse. So we get gamma 5 in a new representation, the same new representation. So now, let's work out in the representation we found what this gamma 5 is. This is going to be gamma 5 equal to some constant, which we're going to choose for our own convenience. Then we have 1 minus 1, I sigma 1, I sigma 1, I sigma 2, I sigma 2, I sigma 3, I sigma 3. And let's just multiply these a pair at a time. So here I'm going to get minus I sigma 1 down here, and I'm going to get plus I sigma 1 up there. Multiplying these two, I get minus, right, sigma 2, sigma 3 is just I sigma 1. So I'm going to get minus I sigma 1 here. And then I get another term in the lower corner. I get a minus from the I squared. Then sigma 2 times sigma 3 is I sigma 1 again, with the minus sign. And so finally, carrying out this multiplication, I get a minus sigma 1 squared, that's minus 1. Sigma 1 squares to the 2 by 2 identity. And then here, this one gives in the upper right corner plus 1. Now, the properties we want for this matrix, right? That's a nice matrix. If I square it, notice that I get what? I'm going to get lambda squared, and then when I square this matrix, I get minus the identity. So the four-dimensional identity. So let's let lambda be I, and then gamma 5 squared is just 1. It's just the identity matrix. That's a convenient property. Also, notice that that means that gamma 5 dagger is going to be I minus 1, 1 dagger. So this is antisymmetric, so it goes to minus itself, but I goes to minus I, and it comes back to gamma 5. So this one coefficient means gamma 5 dagger is gamma 5, and gamma 5 squared is the identity. And those properties will be preserved as long as this A is unitary. Right? If A is unitary, A dagger is A inverse, and so our new gamma 5, say gamma 5 tilde, is A gamma 5 A inverse becomes dagger, so that gamma 5 tilde dagger is, all right, A dagger dagger becomes A, gamma 5 dagger is gamma 5, and this becomes A dagger is equal to gamma 5 tilde, so it stays Hermitian. And squaring it, gamma 5 tilde squared is going to be A gamma 5. I'll leave this as A inverse, and A gamma 5 A inverse. The A's give 1, gamma 5 squares to 1, and then A inverse is 1, and so it still squares to 1. So these properties that we get by choosing lambda conveniently hold for any unitary transformation, similarity transformation of gamma 5. So still a huge number of possible bases for these gamma matrices. And so things we prove using this one representation, which won't be too many things. As much as we can, we're only using the fundamental definition of the Clifford algebra. All of this can be done using only that. But if we need to resort to a particular representation, we can use this one with confidence that whatever we prove will hold even if we do a unitary transformation. So now, I want to construct a series of additional matrices. Oops, I just erased our representation. I'll put it back up over here. So we can take gamma 0 to be 1 minus 1, gamma I to be I sigma I sigma I, and then gamma 5 will be, where did we find it?
I11.
Yeah, I1 here and minus I1 there, which is manifestly Hermitian and squares to 1. Okay, so now I want to define some additional operators from these. So we noted last time that we have the identity matrix, we have our 4 gamma matrices. We can define sigma alpha beta to be the commutator of a pair of these. And notice, if I take a product, gamma alpha, gamma beta, any product of gamma matrices reduces to just the antisymmetric part plus something we already know. So I can write this as a symmetric part, half the anticommutator, plus the anti-symmetric part, half the anti-commutator, is it clear that this is a true statement? This is gamma alpha, gamma beta, plus gamma beta, gamma alpha.
Oh yeah, this is true.
This is you see it.
Minus,
It's just write it out, and you see that the extra term cancels. All right, but then this is just eta alpha beta times the identity. We already know the identity. This is let's see. Let's leave the half. This is our sigma alpha beta.
Yeah.
So the only new thing we get when we take a product of two is this sigma. And that's going to be true for higher products as well. If I take a product of three gammas, gamma mu, say, then the only interesting part is when we look at the anti-symmetric part here. Right? Any symmetric part in there I can replace by an identity, and then there's one gamma left, so I'll just get a gamma, which I already have in my list. So the only new thing we've gotten so far is this, and the only new thing we expect at this level is this anti-symmetric part. Now, what I want to do is argue that this is very similar, in fact, let's say similar enough to gamma 5 times gamma alpha. Now, how do we see that? In fact, suppose I take epsilon alpha, beta, mu, nu on gamma nu. Then that's some anti-symmetric thing. Let me put a gamma 5 in here, and now let's see what that is. Gamma 5 can be written using the Levi-Civita tensor, anti-symmetric symbol. All right, this is now an I times these. But I could also write this as 1 over 4 factorial, I over 4 factorial, epsilon alpha beta mu nu. Gamma alpha, gamma beta, gamma mu, gamma nu. Right? All 4 of these have to be different. There are 4 factorial different ways of ordering them, and since they're different, they anti-commute. Right?
Mm-hmm.
If these are the same, I get 1. But if these are different, if alpha is not equal to beta, gamma alpha, gamma beta has to be equal to minus gamma beta, gamma alpha, because there's 0 on this side. So since this mandates that all of these are different indices, then I just rearrange. Every time I rearrange these, I pick up a sign. Every time I rearrange those, I pick up a sign. So all 24 are going to contribute, so I just divide by 4 factorial, all the different combinations, and I get back to this same thing.
Mm-hmm.
This is just 24 terms, each of which can be rearranged to look like that.
Mm-hmm.
So now, when I put another epsilon like this, I have epsilon alpha, beta, mu, nu. My gamma 5 is I over 4 factorial epsilon alpha, beta, mu,
Nu.
rho, something different,
Oh.
right?
Yeah.
Then,
What?
wait a minute,
What?
what am I doing? No, these all have to be different, right?
Yeah.
Okay,
Rho sigma.
Rho, sigma, lambda, delta.
Yeah.
Gamma, rho, gamma, sigma, gamma, lambda, gamma, delta. And then one more gamma alpha. Or no, gamma nu. Sorry. Gamma. Okay. There we go. All right. Now, these are all different. Right?
Sounds like I like the indices.
Yeah. Good. Okay. So, these indices are all different. So this has to be equal to one of them.
Right.
Right. And so I can move this one over until it meets its match, and it squares to 1.
Yep.
Plus or minus 1. And so up to a sign, I'm going to get an epsilon on the remaining 3 gammas,
Right.
which is the anti-symmetrization that we're after. It's this. Now, we can make this rigorous by working through what the product of 2 epsilons is. The product of 2 epsilons can be written in terms of metric synchronic or deltas, right? And we can write out all 24 terms and do all the sums, and we're going to reach the same conclusion that these 4 indices have to be basically the sum reordering of those indices, which means that 3 of these are going to be alpha, beta, mu, and the last one is going to be nu, and that sum is the trace of plus or minus the identity, and that's just 4 or something. So we're not plus or minus 4. So the conclusion is, without working out the detailed normalization, it's just as good to work with gamma 5, gamma alpha, as it is to work with the anti-symmetrization of 3 gammas. And it's a lot easier because gamma 5 has nice properties. So I'm adding to my list the next one, gamma 5, gamma alpha. And now I can go to a product of 4, alpha, gamma beta, gamma mu, gamma nu, and only the anti-symmetric part can give me something new. And what does it give me?
0.
Why?
Well, you have the 4 of them there, and you change things and do them all.
They better be all different.
Yeah.
You're right there. But what if they're all different? What do you get then? Hint.
The one that we just did.
Gamma 5. It's gamma 5.
Yeah.
Put an epsilon on here.
Okay.
That is gamma 5.
Yes.
So, gamma 5. Now, you got ahead of the game, but what happens if I anti-symmetrize over 5?
0.
Now it's 0, right. In 4 dimensions, you can't anti-symmetrize 5 things. 2 have to be repeated, and you'll get 0. So these are all of the matrices we can build from the gammas, these and their linear combinations. But if we count, right, there's 1 here, there are 4 here. Anti-symmetric indices here give us 6 in 4 dimensions. Here we have 4 different matrices, and here we have 1. And if we add those up, that's 5, 11, 15, 16 different matrices. And these are 4 by 4 matrices. So any complex linear combination of these gives us any complex 4 by 4 matrix. So we can construct any 4 by 4 complex operator at all by taking various linear combinations of these.
That looks a lot like a thing you see in algebra, that Pascal's triangle there. The 1, 4,
Oh, that's
6,
this is. Yeah, it's just the combinatoric factor.
Yeah.
N choose K. 4 choose K. Yeah, it's exactly that. Okay.
So these gamma matrices
Uh-huh.
are gonna form a basis for some. I'm just trying to.
They form a basis for operators on Dirac spinors. Right? Any kind of interaction you want to write in field theory between Dirac spinors and maybe some other stuff, you can write as linear combinations of these. Proving things about these lets us prove things about Clifford algebras. Now, in general, notice that this is 2 to the 4th. In general, if we're in n dimensions, it's Pascal's triangle, right? In general, you have, here we have 4 choose k, the sum k equals 0 to 4. And what is that? Well, I can write that as the sum k equals 0 to 4 of 4 choose k, 1 to the k, 1 to the n minus k, which is the binomial expansion of 1 plus 1 to the 4th, or 2 to the 4th. If I change that upper limit, right, the sum n choose k from k equals 0 to n, by the same argument, it's going to be 2 to the n. So the number of independent matrices we're going to construct in n dimensions, if we have an n-dimensional Clifford algebra, the number of independent matrices we can construct is 2 to the n. And if from our gamma alphas, our basis matrices for the Clifford algebra, we can construct 2 to the n different matrices, how big do those matrices have to be? They'd better be 2 to the n over 2 by 2 to the n over 2, or we're creating, we haven't created enough matrices for those degrees of freedom, or we've created too many. Well, in fact, there is a 2 to the n over 2 dimensional representation of the n-dimensional Clifford algebra, from n gamma matrices. So that if you write the Dirac equation in n dimensions, then the gamma matrices will be 2 to the n over 2 by 2 to the n over 2, and the spinors will have 2 to the n over 2 components. So when we do string theory in 10 dimensions, right, n over 2 is 5, 2 to the 5th is 32. So we will find that spinors for string theory have 32 components. They're big. That's equivalent to, four different Dirac spinors, right? Each 10-dimensional spinor could be broken up into 4 different, eight different Dirac spinors. And that happened by some means of compactification or whatever. Now, the one thing we haven't proved, and it's going to be worth our going through the proof because we developed some technology on the way. We haven't proved that these 16 matrices we've constructed are all independent. And in order for all this argument to hold, we need to prove independence. So let's suppose...
linear independence, you mean?
Yep. Yeah. So let's call these, if we want to refer to all of them, let's just say capital gamma A.
Sure.
Yeah, capital gamma A. Then suppose the gamma A are dependent. Then there exist constants such that A times the identity plus A alpha gamma alpha plus, let's call these different things. C alpha beta, sigma alpha beta, plus D alpha gamma 5 gamma alpha plus E gamma 5 equals 0. So if they're dependent, there exists such constants.
Yes.
We're going to prove that all those constants have to be 0 in order for this to hold, and therefore prove that they are linearly independent.
Right.
You know the argument. So how do we do that? The way we go here is to multiply in turn by each of these things and take the trace. Because it turns out, and we'll show, that the trace of the product of any two different ones is 0.
Mm-hmm.
So first, let's look at, consider traces. So we know that the trace of the identity is 4. No problem with that. The trace of gamma alpha, all right, let me do this 2 ways. And, all right, remember, what I'm doing here, this result, it's true. They're independent. Right? tell you right now. But what you need to do quantum field theory, QED, is you need to be able to take traces of products of gamma matrices. So developing the ability to do that is what we're really after here. But we'll use it to prove this proof. I'll do this one two ways. First, let's look at our representation here. The gamma i's have 0 diagonal, and gamma 0 is 1 and minus 1, so the trace of these is 0, right? Just by inspection in this representation. But notice that the trace of A gamma alpha A inverse by the cyclic property of the trace is equal to the trace of A inverse A gamma alpha equals the trace, that becomes 1 of gamma alpha. So if this representation is traceless, every representation is traceless.
Yes.
So these are traceless. I'll do another argument. What I want to do is insert an identity here. And since gamma 5 squares to the identity, I can write that as gamma 5, gamma alpha.
Mm-hmm.
Now, using the cyclic property of the trace, I can put one of those gamma 5s on the other end. And now, okay, here's something we didn't show. So I think I left this as an exercise last time, so we've all done it. But just to remind you, exercise, prove that gamma 5 anti-commutes with all the others. So do that. That's not hard. The argument is easy because what happens is when you have a product of all 4 and multiply by 1 more, all right, you get a minus sign every time you bring it through,
Mm-hmm.
but eventually that one will, you have all 4 listed here. So if I bring a gamma 3, I bring it in until I hit a gamma 3, and then it squares to 1.
Mm-hmm.
So yeah, all right, here's how it goes. I'm halfway through, I might as well just give you this example. So here's gamma 5. If I have, say, a gamma 2, then I bring gamma 2 past gamma 3 and square it, that's going to be minus I gamma 0, gamma 1, gamma 3.
Mm-hmm.
If I bring gamma 2 from the other side, I gamma 0, gamma 1, gamma 2, gamma 3, now I have to pass gamma 0 and gamma 1, so I get plus I gamma 0, gamma 1, gamma 2 still squares to 1, gamma 3. So I get the opposite sign because I'm passing 2 things instead of 1.
Mm-hmm.
So when I take the anti-commutator, it's the sum of these, is 0. Right? So that's the basic way that this argument works. And you can generalize it to anyone or just try to say how this happens no matter which one I put here and here. Okay, so using that, down here I have gamma alpha, gamma 5. Remember, I brought this gamma 5 off to the right, and now I anti-commute it, so I get minus trace gamma 5, and then here gamma 5, gamma alpha, because I've interchanged these. So going from here to here, I use the cyclic property of the trace, but coming back, I use the anti-commutation of these two. And now this is minus the trace, gamma 5 squared is 1, so I'm back to gamma alpha. And combining these, twice the trace of gamma alpha equals 0, cancel the 2. And we have that the trace of the gamma alphas must be 0. That's independent of representation. Notice I only used the properties of anti-commutation of the Clifford algebra. Well, let's go on. Trace of sigma alpha beta. Let's work on that one. Let's come over here. Now, sigma alpha beta, it's the commutator, right? It's gamma alpha, gamma beta, minus gamma beta, gamma alpha. So it equals 0 if alpha equals beta. So let alpha be different from beta. So this only exists if alpha and beta are different.
Mhm.
Which means that these two anti-commute, and this is just twice gamma alpha, gamma beta. So the trace of sigma alpha beta is going to be equal to
Twice the trace of.
twice the trace of gamma alpha, gamma beta. Now, the trace of gamma alpha, gamma beta, let's see, is that quite right? Yeah, that's right. All right, now let's use the fundamental relationship. This is equal to the trace of, right, using the basic property of the Clifford algebra.
Mm-hmm.
This is equal to
Twice eta alpha
twice
beta
eta alpha beta times the identity
plus
minus
beta
gamma
minus
beta gamma alpha.
Yeah.
So minus the trace of gamma beta gamma alpha plus twice eta alpha beta times the trace of the identity.
Mm-hmm.
All right, and bringing this to the other side, use the cyclic property of the trace. I can interchange the order. I bring this to this side, and I get twice the trace of gamma alpha gamma beta is equal to twice eta alpha beta times the trace of 1, which is 4.
4.
So the trace of a pair of gamma matrices is 4 eta alpha beta. Now, we said alpha not equal to beta, and so that means that the trace of sigma is 0. And we fill in one more. Everybody see it?
It had to be.
Yeah. Well, they're all trace 0.
Yeah.
But, yeah. Why did it have to be? Could you see that?
Well, so the previous trace.
Yeah. Was 0.
And so then
Combined induction, they're all 0.
no. This sigma alpha beta is just a commutator of those,
Yeah.
right?
Yeah.
And so if you have two gammas like gamma alpha, gamma beta, that will right? It's this argument that we've gone through. So you look over there.
Yeah.
And you have gamma alpha, gamma beta,
Yeah.
which is written in terms of eta alpha beta.
Well, the anti-commutator.
Oh, yeah, sure.
The anti-commutator is 1. So this is built out of products of two gamma matrices.
Right, so...
And its trace is not 1.
Right.
It's not 0, right? So the trace of gamma alpha, gamma beta, right, is 4 eta alpha beta. We just proved that.
Right. But I'm saying that you could use the two gamma alpha beta like you did over here,
Mm-hmm.
and then you see, okay, I don't know how to say this, but I mean, I don't see how else it would not have been.
Well, it's true, right? And we just proved it. So
Yeah.
maybe that's enough.
Yeah.
There's a generalization of this proof. Suppose we have a product of any number of gamma matrices, gamma alpha through gamma beta, and suppose we have 2k plus 1, any odd number, the product of any odd number of gamma matrices. What is the trace? Well, the same trick is going to work. I can stick gamma 5 in anywhere I like for free.
Yeah.
And by the cyclic property of the trace, I'm free to place this first one off at the end.
Mm-hmm.
And now, because gamma 5 anti-commutes with any
of these.
of the gamma betas, I'm gonna get a minus sign each time it passes. So I'm gonna bring this through all 2k plus 1, and it's going to give me minus 1 over 2k plus 1 times the trace of this gamma 5 times that gamma 5 times gamma alpha through gamma beta.
Mm-hmm.
And I replace the 1, and I get, that's an odd power, so I get minus the trace of gamma alpha through gamma beta.
Mm-hmm.
And since it's equal to minus itself, it's equal to 0.
Yeah.
So the trace of any odd number of gamma matrices is 0. Which means, since gamma 5 times gamma alpha is 5 gamma matrices,
Mm-hmm.
because this is 4 and there's 1 more, that trace is 0. And then the trace of gamma 5, look at our representation, it's off diagonal, so its trace is 0. So the trace of all of these except the identity gives 0. So now, the next thing we prove is that the trace of the square of any of them is not 0. So if I take the trace of 1 squared, that's still going to be 4. If I take the trace of gamma alpha, all right, I square one of these, then that's going to be eta alpha alpha, that's plus or minus 1 times the trace of the identity. So it's 4 times eta alpha alpha. There's no sum here, just plus or minus 1. So, so I work through them that way. You know, squaring any of these, I always get an even number. So
Is it another 2?
2, is there?
No, it's 4. From there, when you change alpha to beta, beta to alpha, trace gamma.
Yeah, but you
Yeah, I'm
beta
setting
to
alpha equal to beta, and I'm not summing. So that's just plus or minus 1. These two's cancel.
Okay, fine.
Right? So it's
Fair.
just plus or minus 4. So any of these squared has an even number of gamma matrices in it. So not automatically 0, but in fact, gamma 5 squared is 1, so that's non-zero. Gamma 5, gamma alpha times this, well, you interchange the gamma 5 with a sign, the gamma 5 squares to 1, and so it's the trace of gamma alpha, which is plus or minus 4. The sigma alpha beta, all right, we said could be written as twice gamma alpha gamma beta. If we square that, interchange the different pair with a sign, then it's gamma alpha squared times gamma beta squared, so an identity again, up to a sign. And that's traceless. So the trace of the square of any of these is non-zero. The trace of the product of any two different ones is 0 again. So here's the strategy, which I'm not going to have time to run through today probably, but multiply this by each of these in turn. Say we multiply by gamma alpha. Then the trace of gamma alpha times any of these is 0, but the trace of gamma alpha squared is not 0, which means that coefficient has to be 0.
Oh, yeah.
We do that for each of them,
Mm-hmm.
right? And so we
How about the identity?
multiply by the identity. We just showed trace of all of these is 0.
Oh, I see.
So trace of that is not, so A has to be 0.
I see.
Right? So you eliminate one at a time that way. We've just eliminated the first two by, I think, a convincing argument. Gamma 5, okay, multiply by gamma 5. Let's see, get a gamma 5 squared here. The trace of that gamma is 0. Gamma 5 times sigma. Let's see, what happens there? You get two different ones. So, yeah, you know, if this is 1, 2, then this has 0, 1, 2, 3. The gamma 1 and gamma 2 are going to square to minus 1. You're going to be left with the gamma 1, 3, which is a different sigma. So gamma 5 times the sigma is basically proportional to another sigma, which is traceless.
Mm-hmm.
So the products of any pair of these, I think we pretty easily show, are the product of these two is that which is traceless. And so, as an exercise, prove that the product of any pair of these, any different pair is 0, any like pair is non-zero. And that allows you to prove that all these coefficients have to be 0. Okay? Everybody sees the basic argument here. So, proof left to reader, go home and work out the details. But now we have proved that in order for there to be a representation of this Clifford algebra where gamma alpha runs 1 to n, an n-dimensional Clifford algebra, the representation has to be at least 2 to the 2n by 2 to the 2n matrices. And the spinors have to be at least that big. It is not too hard, with a little bit of notational convention, to prove that you actually can write matrices that do that in any dimension. And so now we know how big a Clifford algebra representation has to be in any dimension you like. What we need to do is basically 4-dimensional. So we'll stick to that unless we start trying to do string theory. Okay. So that what we want to do further is to be able to construct vectors. Right, just like we did for SU2. For SU2, we were able to write a
commutator.
A traceless Hermitian representation of a real 3 vector. So what we were able to do was say, so for SU2, we know that if G is an element of SU2, we can write it as the exponential of some I phi over 2 unit 3 vector dot sigma.
Yeah.
So it's parameterized by 3 real parameters, 2 angles for the unit vector, and then 1 angle of rotation around that direction. And we saw that if we let X be a linear combination of the Pauli matrices with 3 real combinations, then that's preserved by these transformations under similarity. So that X prime is GX, G inverse or G dagger. These are unitary. And then this is equal to some X prime dot the Pauli matrices. And the map from X to X prime that we get that way is a rotation by an angle phi around the direction n. Well, we'd like to be able to do a similar thing for the gamma matrices, sigmas. And, okay, here's something that you all should just work out for next time. This would be good. All right, work out the commutator of a pair of sigmas. And my claim is that it's a linear combination of the sigmas again. That's enough of the hint. Now, you can take alpha not equal to beta and mu not equal to nu, but remember that alpha might equal mu or nu, beta might equal mu or nu. So when you interchange orders, you're going to get, let's see, where did I write this? In general, from the fundamental commutation, you can write gamma alpha beta in one order as minus gamma beta alpha plus twice eta alpha beta.
Yes.
Okay, so use this to rearrange. Anytime you have to move an alpha past a mu or a beta past a mu or a nu, you're going to pick up an eta. Right? Otherwise, you can write this as twice gamma alpha gamma beta commutator twice gamma mu gamma nu commutator. So let's just multiply by a quarter here to get rid of those. effectively you can do this where alpha and beta are different, mu and nu are different. Then this is gamma alpha, gamma beta, gamma mu, gamma nu, minus gamma mu, gamma nu, gamma alpha, gamma beta. Now, pass the gamma alpha through the mu nu, pass the gamma beta through the mu and nu, and these cancel, but you picked up a bunch of etas in the meantime. Figure it out. Work that out, right? Find out. You're going to get a combination of etas with pairs of gammas that are going to look like sigmas again. It's going to close. It's going to be a Lie algebra. It's going to be the Lie algebra of the Lorentz group. These are generators of Lorentz transformations. Prove it. Show me on Wednesday. Okay? Yeah. It won't take it too long. You know, it's just, you know, a half page of commutators. So I gotta go. It's Meg's birthday today, and we're celebrating. So
Congratulations, Professor.